Hello, scientists, and welcome back to the Science Lab essay, where we break down science one concept at a time. I'm Selby, and again today we are answering grade 10 Physical Sciences Paper 1, Question 3. This is about motion in one dimension. Now let's explore how it all works. From this question, the engineers at a car company conduct various tests on their cars. During one of the tests, they measure the change in position during equal time intervals. Now, the results obtained are recorded in this table, as you can see. Now, they want you to give the correct term for the change of position per unit time. Position divided by time. What is that term? That is simple. Position, you can see it is measured in meters, and then time is in second. What is a quantity? That will be in meters per second. That will be the velocity. Yes, that will be the velocity. Why the velocity and not speed? It's because when we consider position is specific to the direction, right? Specific to a direction, and therefore that's why we say it is velocity, not speed. So here the answer is velocity. The answer is velocity. Now, number 3.2, the tests. For this test, write down the independent variable. Okay, we have only two variables here. It's time and position. And I must tell you this, always when time is involved, it's one of the variables. Time does not depend on anything. Time does not depend on anything. It keeps moving. Time keeps moving, and therefore it is independent. Always time will be independent. Always remember that. Time is always independent. Obviously, because there are two variables, the dependent variable here will be the position. The position in this case will be the dependent variable, the position. Now, number 3.3, use the information in this table and draw an accurate position time graph on the graph paper. So this question paper have a graph paper. So let's go look for that graph paper at the end of the question paper, and then we use it to draw this graph. Right, here is the graph paper. With the graph paper, you must label everything, the title, the axis, and number in your scaling also, right? And also you must remember your graph must always fill at least half of the graph paper. Make sure the scale that you choose must make the graph to cover almost half of the paper. You see, this graph paper was meant specifically to answer question 3.3. Now, the title of this will be position time graph. And then you write the position time graph. position time graph. You will complete the rest. You know what I wanted to type there or to write. Now you must number your axis, or you must also write the name, the labeling of the axis. The independent variable is always the x. The independent variable is always the x. So this is the time in seconds. Write the units also. This is the time in seconds, right? And then this one here will be what? Position. Just want to write P instead of F. Oh, my pen is misbehaving today. Position. And this position must be in meters. Must write all that. That is all important information, right? Now let's look at the scaling. For our time, you see it's easy, 0, 1, 2, 3, 4. And if we check here, if I take this one to be number 1, 2, 3, 4, it's almost half of the page. I'm fine with that. And then I can just use the main 1 centimeter mark to be my 1 second. And then this one will be 0. I will have 1 here. I will have 2 there. I will have 3. And then I will have 4. Nah? This is time. And then my position starts from 0, 5, 10, 15, 20. Simple again. If it is 5, 10, 15, 20, it's more than half of this page. Then I can still use the main dividers of my graph. It is good. Right. Now I have to plot points, which I'm going to join later. Now, when time is 0 and 0, this is the point. Let me use a different pen. Should I use blue? But remember, you will be using a pencil or a pen depending on the instructions to draw. You will use a pen. You'll have to use a pen. I'm going to mark that point, and then 1 and 5 is that point there, and then 2 and 10, that point, 3 and 15 is that point. This is my 4 and 20, that point. Now I have to draw. Now I have to draw my graph. I have to draw my graph. I want to use a straight line. And then I will start from this point and make sure most of the points are on the line. That is called the best fit. The best fit. Most of my points are on the line. It's, in this case, all of them almost. If you check, it's almost all of them which are on the line. So that's good. Now we have drawn our graph. Check position time graph. Here is the title. Position time graph. And then on the y-axis, we have position in meters. That's the labeling. It's a mark just to label it correctly with units. It's a mark to label our independent variable, the time, with seconds. And then joining, putting some points here and joining them is also 2 marks, right? So there we go. Now they say calculate the gradient of the graph. The gradient of the graph is the slope, the change in y over the change in x. In this case, 3 point, let's write here 3.4. The gradient is what we're going to calculate. Gradient, which is equals to the change in position, divided by the change. The triangle symbolizes change, the change in time. Let me just write t. But position is in full. Let me write this one also in full. Now, the position, it's easy. Just pick any points that are on the line. In case your points are not on the line, in the terms of the best fit, you choose those that are on the line, right? My points are all on the line, so I can choose any. Now, to make it easy for me, I'm choosing the 20 and the 0, which means the first and the last point. So I'm going to say 20. Change means minus 0. I'm choosing this point here and this point here. So I'm going to divide. Here it is 20 for position, and then the time must be 4, so I'm going to make 4. If the position is 0, the time is also 0. So we have 20 divided by 4. Easy, ne? What is 20 divided by 4? 20 divided by 4 is 5. It's 5. But what is meters divided by seconds? That is meters per second. This is the gradient. So the gradient or the slope of this graph gives us velocity, as you can see, meters per second. But that is not what was asked. We were asked just to calculate the gradient, which is our full 4 marks. Each time you have to calculate something in physics, start with the formula. That formula alone has 1 mark. Just 1 mark to copy or remember a formula. You copy it from the back of your question paper, the formula sheet. If it's one of those that are always not given, you remember the gradient is the change in y over the change in x. Always is the slope. You remember that. Then you get your mark. Now, what draw and not to scale a corresponding velocity time graph for the motion. You see, the gradient or the slope of this, the slope here is a straight line. So it means it is constant. It is constant. It's not changing. See, the steepness of the line is not changing. That is the gradient. It's always constant, and that will be 5 as we have calculated. So if we were to draw a velocity time graph for this motion, it means we will have something like this. Not to scale, meaning we don't have to use rulers and stuff. We can just draw random, right? We have velocity, and I said if there is time, time will always be the independent variable. And then we have velocity in meters per second, right? And then we will have a constant, a straight line there that shows that it is constant, it's not changing. And what is the value here? The value is 5. Here you can put your 0, it's fine. But now you see the velocity is 5 and it does not change with time. It stays constant throughout until 4 here. For the whole 4 seconds, this velocity did not change. You can label it and say velocity time graph and give it a title. Okay. Now we are done with 3,5. We are going to 3,6. They say hence deduce the magnitude of the acceleration of the car. They want us to deduce the acceleration. What is the acceleration of this car? Now we have to think, what is acceleration? Acceleration is the rate of change of velocity. It means for there to be acceleration, the velocity must change. If the velocity is not changing, like in this case of ours, acceleration is 0 meters per second squared. Why 0? There is no change in velocity. And if there is no change in velocity, it means the acceleration is 0. No change in velocity. No change in v, which is velocity. That is the reason why we say our acceleration becomes 0 or 0 meters per second squared. Now let's move to the next question. It is this question 3 from a different paper. In this question, we are given an aeroplane which touches on a runway at a velocity of 67 meters per second, as shown. Now, after 30 seconds, the velocity of the aeroplane is now 8 meters per second. 8 at touchdown. Now, the aeroplane then continues at constant velocity. That keyword again, constant velocity. What does that tell you? The acceleration is 0. They even wrote it in capital letters to show you it tells you something. Yeah? Constant velocity, acceleration is 0. Now for a further 800 meters before leaving the runway, the length of the runway is 2,000 meters. Now define a vector. Allow me not to write the definitions. I'll just say it. You know, a vector is a physical quantity that have both magnitude and direction. A vector is a physical quantity that have both the magnitude and direction. Now I can do number 3 because it's calculation. I mean number 2, which is 3.2. They want us to convert the initial speed of 67 meters per second into kilometers per hour. There are many ways that you can do this, but there is a constant that is already there for those that have been working with this, and this is how it was derived or it came to be. We know that in an hour, We have how many seconds? Because we must convert those seconds to hour. In an hour, we have 3,600 seconds. And then in a kilometer, we have 1,000 meters. Right? And then if you divide that, you get 3.6, which is a rate that you can basically use to convert. It's a conversion factor, so to say. You can multiply this to the speed in meters per second to get kilometers per hour. No? You can work it out slow by slow if you want, step by step, if you don't understand this. So therefore, this is the factor that we can use. We can just say 67 meters per second multiply by 3,6 is equals to, or let me write it a bit more professional. Can just say this one is equals to 67 multiplied by 3,6, which is equals to, use calculators, scientists, calculators quickly. Yes, 241.2 kilometers per hour. There you go. Now they want us in 3.3.1 to calculate the acceleration of the aeroplane during the first 30 seconds. Acceleration. What do we say about acceleration? Is the change in velocity divided by time. And therefore you can see here we do have change in velocity. The velocity changed from 67 to 8 within 30 seconds. That is our acceleration, right? So 3.3.1, we are going to, it is always a good practice to write what you are given, because there are also formulas that you can use instead of just saying, I can see it changed from 67 to 8 in 30 seconds, and then you take the difference, you divide by 30 seconds. That will still be correct. But to get maximum mark, or to make sure you get the maximum marks, you see here, the marks are 4. That's a lot of marks for this question, really. A lot. So what you have to do here, you're going to write what you are given. Writing what you are given, there is no mark. I must indicate that. This is just for you to help you understand the question and making sure that you don't make mistakes. So in this case, we were given, I'm going to write, this is the given information. I'm given here the initial velocity VI, which is 67 meters per second. I'm also given the final for the first 30 seconds, right? I'm also given the final velocity for the first 30 seconds, which is 8 meters per second, right? Oh, we are given time because they say for the first 30 seconds. Good. Now, what are we supposed to calculate? Calculate acceleration. Then we can write acceleration is equals to a question mark. This is what we need to calculate. Now, when you are looking for a formula in your formula sheet, You must look for an equation that have all the variables that we are given and the variable that we need to calculate. And only one variable, which is the one that we need to calculate, is the one that must be unknown on that formula. The equation that we are going to look for is the equation that will have the initial velocity, it must have the final velocity, it must have time, it must have acceleration. Because we know all those. It is only acceleration we don't know. So it must be on the formula for us to calculate. But there are some instances where you need to use more than one formula. You find that you don't have one variable, but you can get it using another formula, and then you can do that. Calculate it somewhere, and then come put it on your formula. In this case, it is easy. We know V final, it's there. We are given in the formula sheet is V initial plus A change in time. Only copying this from the back of your question paper, you get 1 mark. Now, let's substitute. Substitution is also important. What is VF? VF is 8. See, we're given VF here. It's 8, which is equals to, what is VI? We are given 67 plus A is what we want to calculate. We don't know A. The change in time, that is 30 seconds. Right. Now we are going to make A the subject of the formula, and from here I must also mention, if you can solve this just by saying A is equals to, and then you write the final answer, that is great. This is not mathematics. We don't really need to see how you solved for A. We just want you to solve for A. If you can do that in your head, it's still fine. But here you can see, if you take the other one, 67 to the other side, it will be 8 minus 67. You divide it by 30, and then you get your answer. And what is the answer, scientists? Yes, it is negative 1.97 meters per second squared. Acceleration in this case is negative y. Acceleration is a vector. If you remember what I said about vectors, especially from the first video, go back and watch that one. It's very important. I said the negative shows direction. So if this was going forward or east, then the acceleration was back. So it was decelerating. It was reducing speed, which is deceleration, consistent with what we see on this here, right? Consistent with what we see here. See, it reduced from 65 to 80. It was decelerating. So we say now that A, therefore A is equals to just 1.97 meters per second squared in opposite direction. In opposite direction. I wanted to write direction there. This is the final answer. You see, there is magnitude, there is direction, because this is a vector. Understood? Yes, that is the end of question 3.3.1. Then we can now go to 3.3.2. Now we want the distance traveled by the aeroplane during the first 30 seconds. During the first 30 seconds, the distance traveled by this aeroplane. Again, using the formula sheet given, and given the information that we wrote, that we are given, and the one that we know now, we can calculate 3.3.2 as follows. We can say is the change in x, which is equals to Vf plus Vi divided by 2. All this is multiplied by the change in t. We are given this formula, and we know it is the change in x that we need to calculate. We are given the final velocity, which is 8. We are given the initial velocity, which is 67, and then 2 is a constant. Time we are given is 30 seconds. That is in the first 30 seconds. See, that's why we chose this. But you can choose other formulas as long as they have what you need. Like, for example, you can choose a formula that now have acceleration. Why? Because you have calculated acceleration already. You know the acceleration or deceleration during this period. Right? It's just that it might be less accurate now because maybe you might have made a mistake or conversions errors in your previous calculations, you see. But it will be correct. It will be marked correct. Right? Now this one, the distance traveled, which is the change in x, in this case, is equals to the final, which is 8, plus the initial, which is 67, all divided by 2. Everything here, we're going to multiply it by 30, which is the time. What do you get, scientists? Quickly. What do you get? Yes, 125 meters. 1125 meters. That is the distance traveled by the aeroplane during the first 30 seconds. Right. Let's go to 3.3.3. Calculate the length. No, the time taken by the aeroplane to travel the 800 meters. Now we need the time taken to travel the 800 meters. You see, what are we given again? During this motion, let me write here, this is 3.3.3. Now, what we are given here is the last stretch, no? This last stretch. This final velocity of 8 in the first 30 seconds becomes now the initial velocity in the last stretch. Okay? We are given Vi, which is 8 meters per second. Just writing everything that you know so that it will help you choose the correct formula, right? Okay, we are given change in x. Sorry, do it like change in x, which is, yes, 800 meters. We were told that in this last stretch, it moves with a constant velocity, which means, acceleration is 0 meters per second squared. Right? And what are we supposed to calculate? Time. Time, t, is unknown. Now, can we get a formula with all this that we know? And the one that we don't know, so that we can calculate it. Is everything here? Yes. Now we have change in, we choose this formula, change in x, which is equals to vi, change in t, or just time, plus half acceleration, change in time, squared. This is the formula that we're going to use. Now, what is the change in x? Change in x is 800 meters. This is the last stretch, which is equals to, what is the initial velocity? We agreed the initial velocity now becomes 8. The time, this is what we want to calculate. And then plus half acceleration. What is acceleration? Acceleration is 0. Because in this last stretch, it moves with constant speed or constant velocity, which means acceleration is 0, and then multiply by time squared. But now, because we are multiplying everything here by 0, everything becomes 0. We basically have 800, which is equals to 8t, which tells us that if you solve, you divide both sides by 8, you get, therefore, you'll find that t is 100 seconds. Always remember to write the final units. You might not substitute the units, but when you write the final answer, you must write the units. It's a must. So this is how we solved the whole problem now. Right. At any time of the video, if we're moving fast, you can pause, try to make sense of the content. Now let's move to the next question. The next question wants us to calculate the length of the runway that is not used when the aeroplane leaves the runway. Now for this one, let me write here 3.3.4. We want the length of the runway not used when the aeroplane leaves the runway. We now know that the runway's length is 2000. We are going to subtract the 800, which it have used on touchdown, and this one that it flown over before touchdown, which we have already calculated, right? The distance traveled by the aeroplane in the first 30 seconds, we have already calculated here. So that length that they want, the length, you can write in full that this is the length of the runway not used. So I'm just going to say the length will be equals to 2000. the total length of the runway. I'm going to subtract the 800. I'm going to subtract the 1125, which we calculated here. And then I'm getting 75 meters. This is the runway length that was never used by this aeroplane. Okay. Now let's answer question number 3.4. Pilots should take weather conditions such as wind and rain into account when they calculate landing speed. Right? Now, how should a pilot adapt the landing speed if the surface of the runway is wet? Choose from increases, decreases, or remain the same. This is question 3.4.1. They want decrease, increase, or remain the same. How should a pilot adapt to the landing speed if the surface is wet? Obviously, if the surface is wet, they will have to reduce or to decrease the landing speed. Why so? Oh, that is the next question. Explain the answer in 4.0. So this one, I'm saying it's going to decrease. Why should pilots decrease their speed if the runway is wet? It's because if the runway is wet, sorry, I'm not going to write 3.4.2. I'm just going to say it, and then you'll have to write it or put it in your own way, in your own words, right? Because you see my pen is not nice, and then if I'm going to write here, it's going to take time, one thing, and also it's not going to appear right, nice. So the reason is, when it is wet, the road is slippery. The road is slippery. Then they must decrease their speed to adapt. There is no, they call it traction. The traction is reduced or limited. There is reduced traction between the tar and the tire. This is the tar, like the runway, the tar road, the runway, and the tire. Because the runway is wet, there is no traction. The runway is slippery. Then they have to reduce the speed. That is if they want to stop within the same distance. If now they don't reduce the speed, it means the distance that is needed to stop will have to increase. So if they need to stop within the same distance, then they will have to decrease their speed because there is less grip. Understood? Capiche? That was the last question of this question 3 of the paper. And with that, scientists, that's how you break it down, one concept at a time. If you enjoyed this lesson, hit the like button, share it with your friends, and subscribe for more science made simple. Until next time, keep questioning, keep discovering.